Hey guys, it's Mr. Sheeline here. This is going to be the video mentioned in the notes that is going to walk through how to read, understand, and answer the questions here on phase diagrams and heating curves, worksheet number 1. Okay, so in this worksheet we are working, as it says here, we're working specifically with ice. We're working with water. And we're starting with this water, we're starting the water at roughly about negative 10 degrees Celsius at a near constant rate of heat transfer. So meaning that we're going to take some ice and we're going at roughly at about negative 10 degrees Celsius, and we're going to consistently add a constant rate of heat to it. So for instance, it'd be like we're going to like increase the temperature, or sorry, we're going to toss, I don't know, like, how to put it? We are going to try to increase the temperature of the water at a constant rate. So we're going to be slapping in a certain amount of energy so that we have a constant increase. So you see the slope here, and the slope here should be roughly about the same. Arguably it is the same. And we're going to see what happens, and we're going to talk about what we should see. So for number 1 here, what kind of phase do we see in number 1? Well, number 1 obviously is just going to be from this point to this point, and what we see here is that it should be a solid. Okay. Now, it's a solid from here, and then how do we describe how the energy is moving it? Well, it's a solid. Well, it's, as we saw in the notes, the way that the energy is moving around here as we're increasing the temperature is that we're increasing the kinetic energy. We're increasing the movement speed of the particles. Okay, that's what's happening. So energy is used to move the molecules faster. There's more kinetic energy. Okay, well, is there a change in the state of matter? No, there is no state of matter change here. It's still just a solid in segment 1, which is again from here to here. Now, in segment 2 here, what is the phase or phases present during this segment? What would be happening? Well, if we checked our notes and we took a look at our notes, here we're increasing the temperature. At this point, what we're going to be seeing here is that this is going to be that in-between. That's going to be us seeing a solid slash liquid, or it's a solid that's turning itself into a liquid. Okay. Oh, and just a reminder, if you want to, like, pause the video at any time if you need to, when you're writing this down, by the way. And then so B, how would we describe? So we've got a solid going to transforming into a liquid in this physical change. How do we describe the energy? Well, again, looking at the notes, what we see here is that the energy is being absorbed. That there is there's no change in the temperature, because if it wasn't being absorbed, then what we'd see is just a constant increase of temperature. What we see here is that the energy is being absorbed. And also that the intermolecular forces are due to the intermolecular forces, the particles are moving further and further apart from one another. Okay, so energy is being stored as potential energy, and it moves the particles further apart. Okay. Now, how do we describe what's happening going from a solid to a liquid? Well, it's melting. Okay, so what's happening there? It's melting. Okay, easy peasy. All right, so then what's happening here at segment 3? Like, what's happening from here to here? What's happening in segment 3? Well, what's happening in segment 3 is that we just have a liquid, that we have the phase state of matter that we have now is a liquid. Okay, and that's going to be on the back side. I just haven't flipped it over, but it's a liquid. Now, when it is, as we see here, the temperature is increasing, so how do we describe the energy? Well, it's going to be the same thing as B here. Okay, the energy is used to move the molecules faster. There's an increase in kinetic energy. Okay, and also an increase of heat energy. And that's what we would see here. Okay. And really that temperature is going to keep climbing right up until it's going to go to this next section, which is section 4. It's going to be from here to here. Okay, so if this is a solid, this is a liquid, and here we saw where the temperature is the same, like the temperature does not change, what do we see happening here? Well, here we saw melting down here because we're going from a solid to a liquid. So here, we're presumably going from a liquid to a gas. What's happening? Here, what we're seeing is we are seeing vaporization. Oh, by the way, section 3 did not have any phase change. So here, the phase change we see here to answer 4C is that we are going to see a phase change of vaporization. Okay. How do we describe the energy? Well, the energy is being stored as potential energy and pushes the particles further and further apart. Okay. So again, 4A, it's a liquid to a gas. Energy is being stored as potential energy, okay, in that we have the reaction of vaporization here. And then lastly, number 5, what's happening there? Easy peasy, we're now a gas. Okay. How would we describe the energy here? Easy peasy. Here there's an increase in kinetic energy, so we have increase in particle movement. And there is no phase change. It's the same, it's not changing. Energy is increasing, okay, but the phase is not changing. Okay. And now we got a couple questions concerning, like a couple multiple choice questions here. So, excuse me. Now we've been, that's right, or first before those. Okay, so then the question for 6 and 7 here. So what is the melting point of the substance? So at what it's asking at what temperature did our substance begin to melt? Okay, if we look at the graph here, if we look here, all we have to do is just see, well, wherever this line is lined up at. It looks like it's lined up about right there. And they're going to ask for the next one too, and it's going to look like it's lined up about right there. So it looks like this substance, and plus this is also water, and we should, or if this isn't obvious, how the Celsius temperature gauge is put together. It's just basically watching water freeze and melt, and then also boil. So at what temperature? What's the boiling point? 0 degrees Celsius. And then it asks, at what temperature is it done boiling? Or sorry, this is melting, this is boiling. At what temperature does it stop boiling? It's going to be 100 degrees, okay? Because it's not until it kind of bumps up here when it's all completely a gas. So it's going to start at 100 degrees. It's going to end at 100 degrees, okay? And so that's how we would answer. You saw that, I'm sure. That's how we're going to answer 6 and 7. So the melting point of the substance is 0, and then the temperature in which it is done boiling is 100 degrees Celsius. Number 8, when is the substance melting, or when the substance is melting, the temperature of the ice-water mixture remains constant because of why? And what it should be obvious is that it's going to be C. The heat energy is being converted to potential energy, breaking the intermolecular forces. So basically it's breaking the forces between them. It's making them move further and further apart. Because remember, the intermolecular forces are attractive. They're wanting to be close to one another, but we're breaking that force and we're pushing them further and further out from one another. And then number 9, now this one's a bit tricky because we really haven't gone over it. And so number 9 is going to be A. And what this question is asking is this, is that here it says in their language, it says that or the language of whoever made this question, it is, when a given quantity of water is heated at a constant rate, the phase change from liquid to gas takes longer than the phase change from solid to liquid. But why does it do that? So the answer is going to be the heat of vaporization is greater than the heat of fusion. Well, what does that mean? Well, what that means is this, that if we were to look at this graph, we see that it takes more time for the substance to go from a solid to, or it takes less time for this substance to go from a solid to a liquid than it does to go from a liquid to a gas. Like we see that. You see how like it takes from here to here, this amount of time, versus say here to here. So we see this takes almost twice as much time to go from a liquid to a gas than it does to go from a solid to a liquid. And so what that should, and again, this isn't terribly obvious, but what's happening is this, is that let's say that in order for ice to go from just for the sake of argument, let's say the amount of energy it takes to go from a solid to a liquid takes 50 kilojoules. Let's just say that, again, for the sake of argument. We haven't gone over what joules are. It's just a measurement of energy. But we're going to say that it takes 50 kilojoules to go from a solid to a liquid. So here is where that energy is being stored. And then as soon as it hits, let's say 50 kilojoules, it will then be, for the most part, completely liquid. As for like over here, if this is 50 and this is about double, to go from a liquid to a gas, it takes, let's say, about 100 kilojoules in order to go from a liquid to a gas. So it just takes longer because if we're increasing the temperature, or sorry, if we are increasing the temperature at the same, or let's see, it's not that we're increasing the temperature, but we are adding the same amount of energy at the same rate. So we're basically increasing, the temperature's increasing at a constant rate, you could say. It just takes a little bit longer for us to go from a liquid to a gas. Okay. So that's why it's A. The heat or the energy required to go from a liquid to a gas, the heat of vaporization, is higher than the heat of melting, which is just the amount of energy needed to go from a solid to a liquid for water. And then lastly, we have this little bunch here. So this is going to be that weird, like, triple point pressure. This is the phase change diagram specifically, where we're comparing pressure with temperature. Now, this seems like it's kind of tricky, but it's really not. I know it seems weird, especially that I've colored it in, and especially because we got these weird lines. That's like, ugh, how do we read this? Don't worry, just remember, go back to your notes and see the notes that were made in your notes. Okay, so we've got these equilibrium curves for whatever this mystery substance is. We have the triple point here. We have the critical point over here. Here is going to be a solid. Here it's going to be in the state of a liquid. And down here it's going to be in the state of a gas. Really no different from what we looked at in the notes the other day. So we're going to be asked a number of questions. Okay, so the first thing you were to do is that you were to label all this stuff, which I'm now showing you and that I've laid out. Okay. The next question is, what's the standard melting point of this substance? So at what temperature will this, when at standard pressure, by the way, which will be just 1 atm, what temperature is it going to go from a solid to a liquid? So all we've got to do is we just got to say, okay, well, we're going to make a dotted line across an accurate level across, or line across here, a little dotted line. Where do we see it go from a solid to a liquid? And it's going to be, we're going to see it on this equilibrium curve right here. And specifically, we're going to see it on that dot right there. And so then what do we do? Well, we will then just see at what temperature is that. And roughly speaking, this is going to go from a solid to a liquid at 100 degrees Celsius. Okay, so at about 100 degrees Celsius, we're going to see the substance go from a solid to a liquid. Okay. Now the next question is, okay, well, again, at standard pressure, 1 atm, 1 atmosphere, what temperature do we see the substance go from a liquid to a gas? So again, following this line right here that we made, at this point, at this equilibrium line or curve, what temperature? Well, plot that there, track her down. It looks like somewhere between 350 to 360, or 360 to 370, sorry, is where we're approximately going to see this material go from a liquid to a gas. Okay. And then the last question is going to ask us basically, well, what's the temperature? What's the temperature to go from, at standard pressure at 1 atm, 1 atmosphere? What's the temperature of freezing? Same thing, it's 100 degrees Celsius. So when we start decreasing, if we were to start decreasing the temperature, we would see the phase change at about 100 degrees Celsius. Okay. Let's see. Now 14 is going to ask us here, and I think I can actually pull this down, yeah. 14 is going to ask us here a question of this. If there was a quantity of this substance at a pressure of 1.25 atmospheres, So we're going to start right here. We're going to we made a line across here. If it's at 1.25 atmospheres, and the temperature is and a temperature of 0 degrees Celsius, okay, what phase change would occur if we were to increase the temperature to 750 degrees Celsius? So it's really saying this. So here's our line up here. I made the line across. If we started here, so if we start with the substance at 0 degrees Celsius with a pressure of 1.25 atmospheres, okay, what temperature, at what temperatures are we going to see these phase changes between, and will we see phase changes when we go from 0 degrees Celsius to 750? So from here to here, what are we going to see? So then we draw the line across, and then we see here that it's going to intersect right here, and it's going to intersect right here. Okay, we'll see that. And then from those points right there, that's where we're going to see our phase changes. And we're just going to drop down to see what temperatures we'll see those phase changes. So from solid to liquid, from this point right here at 1.25 atmospheres, we're going to see some sort of phase change. We're going to see it melting. We're going to see a melting point of roughly about 110, 120 degrees Celsius. Okay. While over here, okay, when we're going from a liquid to a gas, when we're going through vaporization, roughly speaking, we're going to see this at about 550, 560, really 555 to 565. I've got 540 to 550. That might be a little bit too low. But somewhere in there, around 550 degrees Celsius, we're going to see the substance go from a liquid to a gas. We're going to see it vaporize. Okay, so that's what we would see using this graph. Again, at 1.25 ATMs, going from this temperature to this temperature, this is what we see. This is where we see this. These are the temperatures where we would see the phase changes. Okay, and then the next question is going to ask you, well, what's the temperature for the critical point? Roughly speaking, what's the temperature for the critical point? So here's our critical point. If we just simply drop down, we should get something around 810 to 820. Okay, 810 to 820 degrees Celsius is where we're going to see the critical point. And remember, critical point is just where the liquid and the gas have roughly about the same density, and there's really not a whole lot distinguishing it between one another. They're going back and forth constantly, and it's difficult to know which one, what it is at a particular time. And then the last question is it's worded a bit strangely, but let's go through it. So let's say we had a quantity of this mystery stuff, and we started this stuff, we put it at 0.25 atmospheres, and we kept it at a temperature of negative 100 degrees Celsius. So right here, okay, so at 0.25 ATMs, 100 degrees Celsius, so we're right here, so we have a gaseous material. So 0.25, starting there, and then we're keeping it at negative 100 degrees Celsius, so right here. Okay. So, sorry, just felt like filling those in. So if we were to keep it at negative 100 degrees Celsius, but if we were to increase the pressure from 0.25 to 1 atmosphere, if we were to increase it, at what pressure do we see this change from a gas, if we were to increase the pressure from 0.25 to 1 atmosphere, how much pressure in ATMs do we see a particular phase change? And what phase change do we see? So again, we're keeping it at negative 100 degrees Celsius. All we're doing is changing the pressure over here. So if we were to increase the pressure, we would see that we would see a phase change when we reach this, whatever this amount of pressure is. So we mark it, and we make a dotted line across, and we see it matches up right here. Okay. And we'd say that roughly around like 0.3, 0.35 ATMs, atmospheres, we are going to see a phase change from a gas to a solid. So more specifically, we are going to see a phase change called deposition. We're going to see a gas turn to a solid roughly around 0.30 ATMs or 0.35 ATMs. Okay. And that is pretty much it for this worksheet here. So if you guys still have questions for me, if you have a specific question covering anything that maybe you still didn't understand on here, let me know. It's important for us to understand what's happening here. And really this worksheet is now just going to be part of the notes for the most part. I didn't take a grade for this. As of April 15th of 2021, as of today, April 15th, 2021, I didn't take this for a grade. It's now part of the notes. So anyway, if you guys have any questions for me, make sure you ask. I'll see you in the next one.